the diversity of topics and also of places. So I hope you all enjoy these lectures on gravitational waves. So the main purpose of these 5 lectures is to understand essentially, first of all, how gravitational waves are emitted by the coalescence of compact objects. By the way, is this letter visible at the back, or is it too small? Good, I see. No? Bigger? Too small, great, okay. I have to write, yes. Yes, I have to get used to it. So yeah, so we want to study the coalescences of compact objects, which are the main source of gravitational waves that we have seen. But actually, for us, this will be just an excuse to use these signals to essentially probe the universe from the emission until our detectors. So what we will cover first, as I said, is the emission, but then we want to know like what happens to these waves due to the cosmic expansion. And also, what happens to these waves if they encounter potentially some objects, galaxies, stars, other compact objects as they propagate through the universe. We have now 3 operating gravitational wave detectors. LIGO, 2 of them in the US. Virgo in Italy, and Kagra in Japan. So I will, at the end of the lectures, as well, I will be reporting on the current results that we have in terms of learning about the cosmic expansion, but also the universe components. Okay, so and one of the main things that I want to argue that I hope you get out of this course is that actually gravitational waves, and I should say, I'm gonna abbreviate gravitational waves as GWs, okay? Gravitational waves are unique cosmic messengers. And they are unique because of several reasons, but I want to highlight 4 of them just to begin with. The first one is that intrinsically these mergers of compact objects that, by the way, could be black holes or also neutron stars, or a mix of them. So this coalescence of compact objects, they intrinsically occur at cosmic distances. So these mergers happen at cosmic distance. Distances. More importantly, we have the sensitivity to detect them. We can detect them. So if we think of these objects that they come from the end state of stellar evolution, then you could think that we know actually very well, not very well, but we have a lot of information about how many stars they are formed in the universe across cosmic time. And if you think that these compact objects, they are following from the end state of the stellar evolution, then with some time delay, but roughly speaking, we will have a merger rate history of these gravitational waves, a distribution in redshift, set redshift, that does something, roughly speaking, I'm just being indicative here, but have some peak at around redshift 2, and then it decays afterwards. So these are signals that majority of them will come already from quite far away. And to put into context, right now, we have detectors that for signals of about 30 solar masses. So these are the masses of the two objects that are coalescing. We can roughly detect them now up to a redshift of 1. Depends a bit on the mass, but this is just broad numbers with current detectors, these 3 LIGO, Virgo, Cagra detectors at their design sensitivity, which is something that people typically call as A+, advanced LIGO detectors plus sensitivity, which is something that starting with the next observing run in 2027, we will get to that we will pass this peak of star formation, this peak of the merger rate. But when you think of also future detectors, actually they will go all the way to redshifts of 40 in some cases with next generation detectors. So what you see here is 2 things. First of all, that we are going to have a lot of signals at cosmic distances that we are going to be sensitive to in the near term, but also that, and this relates to the topic of interest of some of you at least that were saying, if there is like new signals at higher redshifts, perhaps black holes that coming from not from astrophysical origin, but for primordial origin, we could potentially detect them. Yes, please. Yes, excellent question. So as you can imagine, I'm roughly saying that we are now sensitive to redshift 1. So this is beyond what we are sensitive to. So it's extrapolation. So what we have seen now is that the merger rate is actually increasing, and we have a slope for that merger rate. And then this peak, which is, I mean, also just rough number that I'm putting here, to give a sense, is something that you derive from astrophysical modeling. So we have measured this curve for stars, but we don't know how long it takes from a star to form to make a black hole and merge these black holes together. And please, by the way, if I don't see your hands, shout. I think I really want to hear your questions. So that's one of the things that gravitational waves are intrinsically measuring like cosmic distances. The second one is that, which I think is very important, is that the waveforms of these signals are understood from first principles. And this is something for those of you maybe working with other electromagnetic transients, which is quite unique. Normally, when you think of, for example, supernovae, or you think of other transients, even we know less, like fast radio bursts, it's very difficult to model all the physics involved because you have gravity, you have magnetic fields, you have neutrinos. There is a lot of things. But actually, for black hole mergers, this is relatively simple. You need to use numerical relativity, as we will explain. But essentially, you can get some amplitude of the gravitational waves that we have models for, and we will derive in the course. Specifically, how you can model the first part of the signal as a function of time. And this is important because the fact that we know the shape of the gravitational waves means that we can use this waveform to filter our data and extract the signals. And the important quantity, I guess, for cosmology that we are going to see that is relevant is that the amplitude of the gravitational waves is inversely proportional to the luminosity distance. So from the fact that we know these waveforms that we can use to extract signals, and then we can get this from the amplitude, we can get directly the luminosity distance, means that we have an absolute way of measuring distances in cosmology, which is quite rare. The whole game, though, for gravitational waves, and we will go into all the details, is to get information of the redshift. I don't know if there was a question up there or no. Okay, so that's and also something important related to the waveforms is that if you know the waveforms, also you can use this as a way to test your detectors. So we do have a very good understanding of the sensitivity of our detectors. So we know the selection function of our detectors, and this means that we can then reconstruct the properties of these signals, of the population of these signals from the observations. And normally, from all observatories, they have some selection biases. You maybe detect something more easier than other things, but it's not always so direct to get a properly quantified selection function. So that's 2 of the 4 things. Let me speed up a bit here, but the third one is that actually, once they have been emitted, these gravitational waves travel unaltered through the universe. So once they are emitted, they travel unaltered through the universe, except for gravitational lensing. And this is actually something that comes directly from the fact that gravity is so weak. So it means that generating these signals is very difficult. You need to have black holes that are moving at the speed of light and merge. But actually, once they have merged, it's actually really nice because they are not going to be altered by any medium. So that's different, for example, if you think of other transients that when they pass through the intergalactic medium, they can be scattered, CMB photons as well. Here, for the gravitational waves, they are not going to suffer any of that. And the only way, actually, that you can change these waveforms is if there is some lensing. And that's something that we are going to see in the course. And I guess related to that as well, something that is important is that the wavelengths are of astrophysical scale. And this is something that comes directly astrophysical scale that comes directly from the fact that the size, well, let me write here, the size of the wavelength is actually proportional to the orbital separation. So from here, what you can see is that this is the, yeah. So what this means is that all these are black holes that have, depending on the mass, they can be bigger or smaller. but this is different from other transients in which you can have signals which have a wavelength which are microscopic despite being produced by a macroscopic object. Here, the wavelength of gravitational waves from these compact mergers are going to be always at least bigger than the orbital separation. And what this means is that with gravitational waves, you are probing a frequency band which is much smaller than electromagnetic probes. So from the ground, with these 3 detectors, essentially we are now sensitive to frequencies from approximately 20 to 2000 hertz. And then we can, there is plans for having a space detector, LISA, and that will be probing signals which are actually at much smaller frequencies, from 10 to the minus 5 roughly to 10 to the minus 2 hertz. And we have also can detect gravitational waves from pulsars, pulsar timing, which goes all the way down to nanohertz. For the course, we are going to be focusing on this regime of ground-based detectors, because that's what we have data now and what I think is most exciting, I think, for young researchers at the moment to look at. But bear in mind that there is also these other frequency ranges. And actually now also we have some data from pulsar timing array, which is pretty good as well. So, yes, please. Yes, so something that we are going to see is that the gravitational wave frequency during the spiral is 2 times the orbital frequency, the leading part of the signal during the spiral, and then essentially what you can see is that as they when they merge, the maximum frequency will be roughly comparable to the size of the 2 black holes together. That's more or less where you get at. Yes, please. No, excellent, sorry. Thank you. So the question was if gravitational waves are unaffected by the scale factor. And I guess this calls for me just saying that unaltered here, I was meaning changing the shape. The cosmic expansion indeed where we are? Yeah, here. Indeed changes, affects the gravitational waves. And the direct way to see it is that from the amplitude, this scales inversely with the luminosity distance. So this, if you, depending on the rate of expansion, you're going to have a different amplitude. Plus, of course, gravitational waves, they are also redshifted. And we will see what's the effect of this redshifting of the gravitational waves in terms of the interpretation of the parameters. Good, more questions? Exactly, yes. So what it was pointed out is a bit of more detail of what I was alluding to, which is the fact that your gravitational waves are going to be affected by the redshifting. So your frequencies are going to become smaller because your wavelengths become bigger. And actually, what you can see from here, but we will see this in more detail, is that actually what you are sensitive to, the masses that you detect, are the masses from the original signal that have been redshifted. Thanks. Okay, so just wanted to say a bit of logistics, just to leave it here. So this course that we are going to have, it's based on a longer course that we teach at the Niels Bohr Institute. So there are some longer set of notes, but I will be referring to specific parts of these notes, which and the particular information of that, I have made a GitHub repository, github.com, Ezquiaga, and then is the name of the course, Premiere, on gravitational wave, which I have abbreviated Cosmology. So here, if you Premiere. By the way, I sometimes, well, my R's are very similar to choose and are sometimes a bit confusing. If there is something which is not clear, do let me know. But essentially, here I have posted the notes, which I will continuously extend given the discussions that we have here. I want to target the course to you, so please keep an eye to new versions, which I will highlight. But importantly, there are also, so there is a wiki page where there is a divide of the five lectures. The first one today, it's going to be the motivation that we have just done. Motivation. Plus, what we want to see now are the gravitational wave, like basic properties. And then what we will do tomorrow, it's study in more detail this compact binary coalescence, because it's very relevant in order to understand how we extract the information, to understand why the signal looks in this way, and what is the dependence in all the parameters in order to get this information. And then with this, we will be able to introduce the concept of standard siren, which is essentially the fact that I was highlighting, that the gravitational waves, they carry information of distance, and then there are different ways of obtaining redshifts. And then, well, we will see how long this takes, but in principle, the plan is to then move to gravitational wave lensing, and finally learn about current results and future prospects. So this is the initial plan, but I want to emphasize again that this course is for you. So I want to adapt it as much as possible. So that's why I decided to put materials here in this repository, so there is possibility to changes as we go. So maybe we don't get through all of these. Maybe we have to spend more time in some of these parts. That's perfectly fine. So I see already that you're asking questions, but please continue to do so. And then also here in this page, there are the exercises. At the moment, there is only one related to what we're going to see in more detail just now. And then there are other resources that I will be adding as we go along. Okay. Great. I want to also maybe, before I start with the more formal aspects, get a sense of how many of you have taken a course where gravitational waves were lectured. Can you raise your hand? Okay. And how many of you have taken a course on general relativity? Okay, so everybody has taken a course on general relativity, but not all courses in general relativity contain gravitational waves. Great, that's very useful to know. Thank you. Okay, so you can imagine that this is, and I guess this happens with all the courses. This is 5 lectures. It's impossible to really go over all the details and derivations. So there are many things which would be we will just leave for you to explore. But I guess the first question that we need to address is what are these gravitational waves? And the answer actually is very simple, although it's quite deep. But these gravitational waves are linear perturbations of space and time. Okay. That, and this is something that I've already alluded, but they propagate through the universe. And then the way they propagate through the universe actually is detected by the theory of gravity, that throughout all the lectures we will be assuming is general relativity. So then the gravitational waves, they propagate through the universe according to Einstein's field equations. Okay, so let's see in a bit more detail what this long sentence mean. And the first part, I guess, is here there is reference to space and time. So I guess you all have taken course on general relativity, so you know that space and time is described by a metric tensor, where we will be restricting to 4 space-time dimensions, so 0 for time, and the rest components for space-like components. These signals, they are linear perturbations. So what this means is that we can take this metric perturbation, this metric, and we can decompose in 2 terms. One, which will be the background metric, and the other one, which are our gravitational waves, that we are going to call h mu nu. So the condition that these are linear perturbations means that in some, the amplitude of h mu nu as a function of the spatial components, space-time components, sorry, has to be small compared to the amplitude of the background metric, from the background. So that's the mathematical part, and then the last element is how they propagate. That is through following the Einstein field equations. And that's going to be actually that's the part where the cosmic expansion, lensing all comes into play, as we will see in the next lectures. but the Einstein field equations can be described in terms of the Einstein tensor, which is R mu nu minus 1/2 G mu nu R, where this is the Ricci tensor and the Ricci scalar, and this is equals to 8 pi G T mu nu. Here, I'm taking that the speed of light, I'm setting it to 1. If not, there would be here a factor of c to the 4. Okay, so these are the equations from Einstein field equations, but we have a simplifying assumption, which is that these gravitational waves are small perturbations. So what we can do is that we can divide this equation in different terms. The first one would be the Einstein tensor for the background metric. So that's why is the 0th order. So that's the first thing that you have. And this only depends on the background metric. So this G with a bar on top, that's the background metric. And then we can get corrections to these Einstein field equations. The first correction will depend on the background metric and the linear perturbations. And then you can have further corrections, which also depend on G, H squared. So the main idea here is that from the first term, you get the background. So you solve this for a given energy momentum tensor, and you get G mu nu. And then this is what we will be focusing on in the course, which is the first term, which gives us the leading order gravitational wave. Higher order terms we will not include. Yes, please. Sorry. Yes. What I'm saying is that in the course we don't care about this. So we are going to just be focusing on solving this first term that only has terms linear in the perturbations. Yes, yes. So as the space-time is changed in a more strong way, then this assumption that you have like these linear perturbations stops being valid. And in fact, the very fact that we are dividing this in two terms stops making sense. So actually what you need to do in those cases is to study just the metric evolved in a strong field. There was another question. The same question, great. Yes. The energy momentum tensor is actually associated with the square of the linear perturbations. But yes, maybe I should, thanks for that. I should not say so abruptly that we are neglecting this, but what I want to say is that what I meant is that we're going to be focusing essentially on the emission and propagation, and to study that, the equation that we will care about is this one. Yes, but these terms are important, yes. Thanks for that. Good, okay, so we want to study this this equation here, and for that we are gonna do it we are going to study this in vacuum first, so without sources, and then we will add sources. But the first thing that we want to do is to look at the propagation without we want to eliminate the sources just to get a sense of what are the main properties of these gravitational waves. So the equation that if we need to solve, it's the linear perturbations of the Ricci tensor equals to 0. And this is because the Einstein field equation, when you are in vacuum, you don't need to take into account the Ricci scalar. So what you would need to do to get the equations is you need to express the Ricci tensor in terms of the metric and its derivatives, and then you need to expand those at linear order. That's something that I'm not gonna do in the lecture, and just give you the result. But we need to make a couple definitions. So there is a quantity that is gonna be very useful for us, which are the trace reverse perturbations, which are essentially defined as our metric perturbations, where we subtract the trace. And you will see in a second why this is relevant, but just so that you have all the definitions in place, the trace is defined as the contraction of the linear perturbations with the background metric. And then also we have the notion of the inverse metric. Which just comes from raising the indices, and to linear order, you have that G mu nu is equal to G mu nu with indices on top, minus H mu nu. And then also we have that H mu nu is equal to G mu alpha, G nu beta, H alpha beta. So if you use all of these definitions, expand this Ricci tensor to linear order, and I was forgetting, use the Lorentz gauge. Which just fixes the derivative of the covariant derivative of the perturbations contracted is 0. Then once arrive at the equation, which is gonna be fundamental for the rest of the course, which is that the propagation is given by box H mu nu times 2 times R alpha mu beta nu contracted with H alpha beta equals to 0. And here, box operator is the contraction of the covariant derivatives. So that equation there is what we need to solve if we want to know how gravitational waves propagate in a curved background. And it has a lot of important information, but the first thing that you can see is that the propagation, the first term, this box operator, includes covariant derivatives. And the covariant derivatives, if you remember, they include Christoffel symbols. And the Christoffel symbols, maybe I should write them in case you don't remember. I can do it like this. the Christoffel symbols, they depend on the derivatives of the metric, G mu. G mu beta minus the beta G mu nu. So the important thing here that I wanted to highlight is that this first term is telling us that the derivatives of the background metric, here you see that all of these metrics are for the background, affects the propagation. So this is, for example, when it was asked why, if the scale factor affects the propagation of gravitational waves, it will actually do appear because of these covariant derivatives that you have there. Is this clear? Yes, sorry. Yes, sorry. Thank you for that. There should be a bar on top. Yeah, and then, yes, and then so it's telling us that the propagation of the gravitational waves is going to be sensitive to couplings to the background metric. And then the other important aspect is that this term here, which is the Riemann of the background, the Riemann tensor of the background metric, this is going to contain things that goes with second derivatives of the background metric and also first derivatives. But what is interesting is that this term can change, can have effects in the polarization. Although this is something that we will not, as we will see, is not relevant for most of the astrophysical scenarios, but it's important to know that that this term can lead to polarization mixing. Okay, are there more questions here? Yes. No, sorry, yes. So the Riemann tensor is proportional to derivatives of the Christoffel symbol, the Leibniz-Civita connection, and the Christoffel symbols square. So this is linear in first derivative, and then you get second derivative. Thanks for the question. Yes. Yes, so this is the R bar is the Riemann tensor of the background metric, which actually, I don't remember from the top of my head the exact definition, but it's essentially just a combination of derivatives of the Christoffel symbol that you have defined here, and then the terms square. Okay. You can also define it from the commutation of covariant derivatives. I can look it later if you. Good. Okay, so we have an equation, but what do we learn from this? So we have seen that these tell us that there are some couplings with the background metric, but what else can we see? And something which is, which is even more fundamental is like, if we can really, how can we really make this decoupling of the background and the gravitational waves. So for that, what we are going to do is to study the propagation of the gravitational waves in the short wave expansion. Let me erase this. So we want to have a way of distinguish the gravitational waves from the background, which is unambiguous. So this is a problem, by the way, that in flat space one does not have, because in flat space the background is fixed, and then the waves are whatever are changing. But when you have a background which can evolve, then you need to have some way of distinguishing between the two components. So essentially, I'm rewriting the definition that we had before. The metric is our background, which depend on x. This is what in flat space-time, this will be just the Minkowski metric, which is fixed, but we are in a situation in which this can change. And also we have the gravitational waves. So the approximation that we are going to make in order to solve this equation is that we are going to assume that the length scale of the background is much larger than the wavelength of the gravitational waves. So the length scale of the background is much larger than the reduced wavelength. So that's the regime that we want to pay attention to. And in that regime, what we can do is that we can solve this propagation equation that we have over there. We can solve it using the following answer. So we are going to assume that the shape of our gravitational wave is the real part of a tensorial amplitude times some phase. But, so this is our answer. This is essentially just a plane wave. But what we want to see is we want to make the answer in which this wave has a phase. So it has a phase that changes much more rapidly than the amplitude. So the way that we are going to do that is we are going to introduce a parameter epsilon, which is dimensionless, that then we are going to make this parameter go to 0, just a second. And then we are going to, one can construct this answer iteratively, also adding corrections in the amplitude that are proportional to epsilon, and then epsilon square, etc., etc. Yes, there was a question on top. No. Well, it's essentially the curvature of a space-time. What? Well, not exactly. I mean, but I mean, you can think of like essentially what we are saying is that if you have some background in one dimension that changes over some distance, that then on top of this background, there are the gravitational waves, which are small much shorter scale. It depends on the, I mean, you can, I mean, this is more of a formal definition, but like, yeah, I mean, for example, in cosmology, you could do it in terms of the horizon distance. Yeah. Yes. Sorry, so this is what the question that it was asked from the top of is the length scale. So what I'm saying is that this, if this is the whole perturbation of the space-time, LB corresponds to the length scale in which the background changes, and lambda is the length scale in which the gravitational wave changes. But as you see here, actually, from your questions, you are getting at a deep point, which is that intrinsically, actually, all we have in general relativity is the metric that changes. So what we are doing actually is trying to find ways to separate the two different components and analyze independently the gravitational waves from the background. So the two assumptions that we are making is that these perturbations are linear, so they are small. And now what we are making as well is that we are saying that the wavelength, the variation of this perturbation is at a scale which is different, and that's why we can distinguish one from the other. More questions? Okay, so actually the exercise that I'm proposing that you do is essentially taking that propagation equation, using this ansatz, and then deriving the following properties. So I'm gonna give you the properties that one derives, but I think it will be good if you have time that you make it yourself the calculation, because that's something which I think is very instructive. But the main idea, just so that you follow, is that we have an equation that over there, we have an ansatz, and then we have this dimensionless parameter epsilon, which we want to take the limit in, which is very small. So what we are going to do is we plug this ansatz in the equation, and then we solve for different orders of epsilon. The orders in epsilon, which are smaller, sorry, the 1 over epsilon being higher, then that's the one that is going to contribute first. So schematically, if we take that equation, we are going to plug in our ansatz. So h mu nu, epsilon, h mu nu first correction, blah, 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 e to the I theta divided by epsilon. That's the first term. And then you have the second term, which is the Riemann of the background curvature. And then one has, again, A alpha beta, epsilon, the first correction to the amplitude, dot, 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 and then e to the I theta. So that's the equation that we have that you will be working on. And then you can expand this equation, and then you get the different orders. The first one is 1 over epsilon squared. That will be the largest one. And this, you can show that what you would get is something that goes with the derivatives of the phase contracted with each other. And you can see that because you have 1 over epsilon term, it's only coming from the exponent of so from the phase of the plane wave. So every time you get a derivative, you pull one of those back. And then from this equation, what you get, you can rewrite this equation as the background metric, G mu nu, K mu, K nu. And here I'm realizing that I forgot to define the wave vector here. The wave vector, we are defining simply as the covariant derivative of the phase, but because the phase is a scalar, actually this is just the partial derivative of the phase. So that's the wave number. And we are going to define also the polarization tensor. So the polarization tensor is going to be just decomposing all of the amplitudes in terms of a scalar amplitude and polarization tensor epsilon mu nu. And this has the properties that we are defining, which is that it is normalized to 1. And here with the complex conjugate, 1, although this is a detail, but anyhow. And then the scalar amplitude, and I hope you can see over there, but maybe I need to put it a bit up. The scalar amplitude comes from the square root of the contraction H mu nu, H mu nu. So these are just definitions, but the important thing is the physics that we are getting from the equations. And at leading order, actually what we are getting is that the gravitational waves, they follow null geodesics. So that's, so we are finding here that the wave vector is null, which is essentially this definition here. If you take the covariant derivative of this expression, then what you get is that also it follows null geodesics. So this is the other important relation. So at leading order in the propagation, gravitational waves follow null geodesics. Yes. Yes. Which equation? This one? Yeah, so that's what you need to do in the exercise. Essentially is just, this is the overall equation. And then what you need to do is, here you have different terms. You have 1, 2, and other higher order terms. Here you have all the other higher order terms. So you need to expand this. So here, essentially this part here, actually you don't need to do anything because this is just a multiplication. But then here you have the box operator, which is the contraction of the covariant derivatives applied to the whole thing. So essentially what you need to do is apply first one time the derivative, and then you apply twice the derivative. And then what you need to do is you collect the terms that are more relevant. And you will see that the terms which are proportional to 1 over epsilon squared are the most important because this dimensionless parameter epsilon is small. Yes. Yeah, I think, yeah, but very good question. I think hopefully if you sit down also, you will see that the math actually is not very complicated. But it's good to derive these properties. At second order, what one get is the following equation. H mu nu, ta-da-tan, theta, H mu nu, and then H mu nu box theta equals to 0. So this equation, this is what you would get at next order. And from here, actually, one can derive two equations. One is that the number of gravitons are conserved. So this is the equation that you can get. And to get this equation, you need to use these definitions of the amplitude that I was writing here. But I say that, so this is conservation of gravitons. And this is because you could think of this term here is as if this was some current J. Anyhow, what this is telling you is that through the propagation, you don't actually create or lose gravitons. And then the other important, so this is one of the equations that you get at this order. And then the other important equation that you get at this order is that K alpha contracted with the covariant derivative of the polarization tensor, this is 0. And what this means is that the polarization tensor is parallel transported. So if you remember from your general relativity courses, this is essentially the definition of that. Polarization tensor is parallel transported, which also means that through the propagation, essentially you are not changing the polarization content. Are there questions? Yes. One there and then there. Yes. Well, yeah, probably this is a overuse of language. I think actually what you said of just making the particle analog of the wave, that's why we are using this terminology. But the important thing is, yeah, this is telling you that this is telling you like that you are not creating gravitational waves if you want as they propagate. The only thing that you can do is you can focus them or unfocus, but you cannot create more. That's the main point. There was a question on top there. Yes. Yes, so that's a very good question, but you need to remember that we are at this order in the expansion. We are making an expansion, a short wave expansion, and we are actually the leading order part, which is what people call geometric optics, and at that limit, this does not happen. But actually what I'm going to say next is that when you go beyond geometric optics, actually you can have corrections to this. Okay. So that's, yeah, so these are well, there is one property, one additional property that we need to look at. So essentially, we've learned that gravitational waves follow null geodesics and that their properties, in terms of the number of, of them that there are, doesn't change, and also the polarization is parallel transported. And if we use the Lorentz gauge condition, what one finds still at this order of 1 over epsilon, what one finds is that the polarization tensor is perpendicular to the propagation. So what finds, and this is perhaps one of the simplest to derive, mu alpha, is that this is 0. So polarization tensor is orthogonal. Orthogonal to the propagation. So this is, as I said, these are the main properties of gravitational waves when we restrict to what is known as geometric optics. But if you go to the next order, which is epsilon 0, then what we see, so this is beyond geometric optics. Is that for the first time, the Riemann tensor actually comes into play. And you will find that you will get this equation, which is a box operator of h mu nu, 2 times r alpha mu beta nu, alpha beta, and then I 2 times k alpha covariant derivative of alpha of the first order correction, and then h mu nu, the other correction, and then we have k alpha contracted with k alpha of the second order correction, and then this is equal to 0. So one thing here is that, so this is the equation that you get at order epsilon 0, that at face value includes A, the first correction, and the second correction. But you may notice that this second order correction actually is proportional to the contraction of k alpha with k alpha, which is essentially this condition that the wave vector is null. So therefore, that last term does not contribute. So what this is telling us also is that, and actually this is a recursive property. So if you were to include higher order terms here, what you find is that the next order correction, it only depends on the previous one. So here, what this equation is telling us is how the first order correction is being sourced. And then, so this is the equation from the propagation equation, and then from the gauge condition, we have H alpha, nabla alpha H alpha mu minus I to the K alpha H alpha mu 1 equal to 0. So the important thing is that beyond geometric optics, this term, this first order correction, absorbs the small effect of the Riemann tensor. So the Riemann tensor that we had in the equation, in the propagation equation, it's absorbed by the first correction. And this term actually has, broadly speaking, two effects. The first one is that for the if you have terms which are diagonal, meaning that this contributes this contraction of the Riemann with the H alpha mu nu. Well, you can see here, sorry, maybe it's easier. For the components here, which are proportional to the components of the first correction, this essentially actually is acting as an effective master which is actually can change the notion of particles. And you can see that it's an effective master because there is amplitude. The first correction relates to the leading order amplitude with a complex, number I. So this is a correction that is where we are here. If you have something which is complex, you can put it as a phase there. And then the other effect, the non-diagonal, can lead to the polarization mixing that I was mentioning before. So I think these effects are interesting, but actually what we will see is that for the context of cosmology, just because of the huge difference in scales between the curvature of the universe and the wavelength of this gravitational wave from compact binary coalescence, actually, we don't need to worry about beyond geometric optics corrections, and we can solve everything in geometric optics. So I should pause here in case there are questions. Yes. Yeah, so I was being schematic, but what I meant to say is that despite just, so you see here that I'm expressing these terms, the corrections, as amplitude corrections. But I wanted to make the point that actually these amplitudes can be complex numbers, and you see that because you are relating here through the imaginary number, and then if you have some contribution which has an imaginary component, this can be expressed in terms of an amplitude and a phase. So these corrections can change also the phase of the gravitational wave. And effectively, this is as if you had the first order term in some way behaves as a master. Maybe I'm adding, maybe I'm going 2 steps beyond, but I just thought to mention that yes, you need to work out a bit more the expressions to see that. Yeah, maybe we can discuss more on this. Yeah, it's not part of the main course, but I thought to mention maybe. Yes. More questions? Okay, so I think what I want to do last is also just remind you about some of the properties So we have seen the gravitational waves propagate that in geometric optics. So that is when the wavelength is small compared to the curvature of the background, that they follow null geodesics. But here I'm talking a few times already about the polarizations. So I think it's worth reminding you about the basic properties. So we have that our gravitational waves are described by h mu nu, which is a symmetric tensor in 4 dimensions. So this has 10 independent components. We have talked also, so if you think of the tensor as being a matrix, if it's in 4 dimensions, 4 by 4 is 16, and then because it's symmetric, you are down to 10. But then we have mentioned also that we are fixing the Lorentz gauge, which is killing us 4 additional components. So we are left with 6. But actually, there are only 2 propagating degrees of freedom in general relativity. There are only 2 propagating degrees of freedom. So the way actually to fix those propagating degrees of freedom depends on the situation in which we are. But there is a situation that in which if we are in a global vacuum spacetime, and then we are in a asymptotically flat space, plus then one can do is actually fix the 4 other remaining residual gauge conditions so that the metric perturbations are transverse and traceless. So this is a choice that is typically done in the gravitational wave community, which is fixing the temporal components to 0 as well as the trace. And if you look at that in terms of the matrix, I should put it here, I guess. Well, let me just make it here. So if we think of a matrix, the first 4 components will be 0 because the temporal part is 0. And then if we fix this propagation that we have seen that is orthogonal to the propagation direction in the if we fix the gravitational wave to propagate in the z direction, then the only propagating modes that we have can be defined in terms of H plus and H cross, which appear in this matrix in such a way, that it preserves that the metric is transverse and traceless. So this is a choice for fixing the gates, but this is a choice that is common, is the most useful for gravitational waves, and what we will see tomorrow is how this H plus and H cross, how they are sourced by the coalescence of compact objects. But these H plus and H cross, they need to follow all these properties through the propagation that we just derived today. Okay, are there more questions? I see some people thinking more. Okay, so maybe so that you have this in your head for tomorrow already, let me just say in 1 minute what we will be doing. So essentially, what we have done now is seeing the properties of these gravitational waves that they are propagating through the universe, but we were taking this propagation to be in vacuum. And without saying anything about how these signals will be sourced. So what we are going to do tomorrow is to focus specifically to the case of two compact objects which are coalescing, and then what we will be looking is at how these signals are generated. So what we will need to do is to take the propagation equation and then include some energy momentum tensor from the source. And then we are going to see how this h mu nu depends on t mu nu. And then we are going to specify specifically for a t mu nu that comes from two point masses. And this is going to give us the expressions for H plus and H cross, which are going to be the basic building block that we will then could use to infer cosmological properties. Great. Any final question? Good. Please, whenever I'm here, if you have more questions, come and ask. You need to make the most out of it. And also, I forgot to say something as well that I guess connected to what Rogerio was saying at the beginning is that, I mean, one of the best things of these schools is actually your colleagues that you are taking the course with. So do interact with each other, and because you're going to be colleagues throughout your career. And I think, it's one of the things that you can get out of the school. So, for example, for the exercises, I encourage you to work in groups, discuss, build friendships. Thank you so much.
Okay. Thank you, Jose. Are there more questions for Jose? People ask lots of questions. Yes. I have a simple question. Is the wave equation gauge dependent?
The wave equation?
Yeah. You picked a gauge for age.
Yes.
Can you choose another gauge and then things can change, or they're gauge independent? I don't know, really.
So I was choosing the Lorentz gauge to get this expression.
Yes.
If you choose a different gauge, then you may have different combinations of the Riemann and there. Yes.
Okay.
Yes. Yeah.
More questions? So I want to remind you that, as Jose was saying, if you want to work together, there is space on the first floor. There are desks, tables actually, that you can use. So the first floor is the ICTP-SAIFR, and there are several desks, and you can stay there. And we don't close here, so it's 24 hours. I'm not saying that you should stay, but just to let you know that if you want, you can, okay? So, right, so if there are no further questions, let's thank Jose and all the speakers of today. Thank you.